Okay, so this is going to be the final part 3 part of the solution chemistry, chapter 8. So here is where we're going to be talking about concentration. And you have to forgive me if some of my animations aren't exactly, on par here. I didn't thoroughly go through all of these edits. I don't, but with all these animations, and you'll see what I mean, it can get it can get a little heady. Anyway, let's talk about concentration. We're just going to dig right in. Generally, what we're going to be talking about with respect to concentration is the amount of solute versus the amount of solution. And the solute, again, is always going to be in less amount relative to that of the solution. Okay, so I think that's always going to be important. If all of a sudden you're going to get very high amounts of solute and extremely low amounts of solution, then you're going to have a switch up, really, of what you're calling the solute and the solution. And so it won't matter anyway. The nomenclature then, or the assignment of what is the solute and what is the solution, would then change. So concentration is always going to be fixed, solute versus solution. And these are especially useful if we're referencing volume. Okay, so we're going to start talking about molarity. And again, the lab simulation on molarity that you guys will have to do and that is assigned has everything to do with concentration then in terms of molarity, right? And what is molarity? Moles of solute versus liters of solution. So molarity is not grams of solute, and molarity is not, I don't know, picoliters of solution, although you could probably argue that it could be if you just have the right scientific notation and stuff. Because guess why? You can have P for pico and just like M for milli, right? In this particular case, you have millimoles of solute versus liter of solution. But again, you would always be using, actually you probably wouldn't even use P for the pico then. You always want to have liter on the bottom. So even if you're dealing with picoliter, get it into liter. If you're dealing with milliliter or deciliter or centiliter, whatever it is, get it in terms of liters and always have moles as your units of solute. So here's the typical ones. You have molarity or you have millimolarity. Here would be a representative example. What is the molarity of an electrolyte solution prepared by dissolving 5 grams of magnesium chloride in 500 mils of water? So what do? You must use molecular weights of atoms. You must use conversions, in other words, milliliters to liters, and you must understand the molarity equation. So the first thing that I would do is consider the molecular weights of what I'm considering to be the solute. The solute in this case is magnesium chloride. Magnesium chloride is comprised of magnesium, as I show here with this molecular weight, right? There's 24.31 grams per mole, and with chlorine, it's 35.45 grams chlorine per mole, and that will constitute the molecular weight of the solute, which is 95.21 grams per mole. Remember that you have 2 chlorine atoms comprising the solute compound. 95.21 grams per mole is the molecular weight. Now, if that was to be dissolved in water, which that's what you're trying to prepare in this particular problem, then you know that magnesium and chloride are going to dissociate. They're going to become ions. You have magnesium cations, right? And then you have the chloride anions. You have 5 grams, right, of the solute in 500 mils of solution. Let's get that into the liters. Remember how I talked about the importance of the liters versus mils, or what other kind of volume unit. You got to make sure that you have moles of the solute, not grams, okay? The molarity or millimolar or millimolarity is moles of the solute, not grams per solute or milligrams. So you just use your stoichiometry, you get your dimensional analysis correct, and then you're left with 0.0105 mole of magnesium chloride per liter of solution. You can also write that as 105 millimoles, okay? So I think that is really important. Actually, in here, this is just a slight typo here. There should be a decimal point. Anyway, not a big deal. I'll fix that on the slide deck, but you can see that, the concept is there. You set up your equation, you know what your relationship of all of these units are between mils and liters. You know, you're trying to get into moles. That's the major take-home point here. So the molality instead would be moles of solute per kilogram of solution. That's useful, usually if we're using mass. So percent concentration. Let's also talk about, this is another way of expressing a concentration using percent concentration of parts of solute versus parts of solution. And you always multiply by 100. So way back in chapter 1, I think maybe even some chapter 2, but definitely in chapter 1, we talked about the concentration in terms of percent, right? Like how many students, what is the percentage of students if there's like, I don't know, 50 students and 32 of them get A's and the rest get whatever else. What would be the percentage of A's then in the class, right? You do 32, divided by the whole of that, and you come out with your percentage. Same thing here. But if we're talking about mass or weight percent, then we have to specify. So we have percent, which is mass or weight, and usually this is the nomenclature. If it's going to be a mass percent, you'll usually see M per M. If it's weight percent, you'll see either just percent weight or percent W, or you might see weight per weight or W per W. I mean, there's a lot of different ways that this can be expressed. As long as it's clear from the rest of the problem in which you're working on or information that's available to you, then you'll be able to understand it. But now here is the major point. The grams of solution, okay, if we're talking about mass here or even weight percent, is going to be the combination of the solute plus the solvent, okay? So this is not just solute per solvent. It's important to make sure that you have the solute plus the solvent combined, and then you have those times 100. So how does this make sense, and how do we even get this? Let's look at, the difference between non-fat and 2% milk fat. In this situation, with you have 0 grams of milk fat and 100 grams of milk solution. And by the way, I'm just arbitrarily picking 100 grams, okay? It won't matter. I'm trying to do that because we have a percent, and percent means by 100 by definition of the actual quote unquote percent. So that's why I'm deciding to use, you can use 100% or you can use 100 as just the bulk denominator there as your default base. So 100 is our base. In this particular case, 100 grams. In non-fat milk, that's 0%, so you have 0 grams of milk fat, right? But what does that truly mean? You have 100 grams of solvent and you have 0 grams of milk fat, and then 0 grams of milk fat, which I'm referring to here as the solute, okay? So that's how you have non-fat. 2 grams of milk fat and 100 grams milk solution. Again, 100 is the base. We're doing this percents. Then we know that 2 grams of that solute is going to be milk fat. 2 grams of milk fat, which is the solute, plus whatever is not milk fat, which is going to be 98 grams of whatever else that milk is comprised of, which we're calling the solvent. So that is the example, and this is how we're able to express the differences, for instance, between non-fat and milk fat using some equations involving the grams of solute and solution. So whenever we say it's 2%, usually you'll see W per W, maybe on the container packaging. You might see that again. It's just a way of expressing mass percent, okay? So it might be percent mass, it might be M per M, weight per weight, or just weight, or it might even be just percent W or W per W. All of those, it's pretty clear. Now, let's look at volume percent. So instead of mass, let's look at volume percent with respect to, again, percent concentration, recognizing that we're still holding true that it's always solute per solution, okay? Again, it's a percent kind of thing, but let's look at this. Liquids and gases, percent, and it's V per V, okay, would be the nomenclature here that we're talking about. Milliliters of solute versus milliliters of solution. We're using milliliters just because it can be a little bit easier to measure liquids using volume metrics, right? Sometimes it's easier to use gases. Gases can also be done as well with respect to masses, like on the previous slide, but in this particular case, we're using solutes and we're using solvents in the milliliter unit. And again, you just have mils, just make sure that you're talking about the same thing and you're able to get there. So here's the problem. Determine the fractional volume of oxygen and inert gases, I have this quote unquote other, in a nitrox mixture comprising a total of 78% volume, okay? So 78% of that composition will be nitrogen. And I apologize for the English here. I'll edit that whenever I publish these slide decks on the ACE system. But again, the nitrox mixture, that's something that scuba divers can use. It's just a little bit enriched in oxygen, and it's just, it's different than air. It's supposed to give you different benefits in terms of downtimes and how you feel overall whenever you're done diving. I can attest to that because I am nitrox certified, and it does make a difference. So anyway, the whole point is you have 72% other, total gas. All of this stuff is going in here. You have other plus 78% is 100. You have 22% then of other. And I need to change 72 there as well. Anyway, I will. The whole point is the 22 mils of other divided by the 100 mil gas solution would be the 22 mils of solute, because you're looking at the fractional volume of oxygen and inert gases. Again, if you have a total of 78% of nitrogen, then the only other amount, 100 minus 78, is 22. That's where I'm getting this 22 from, right? And this is where we're trying to get the volume percent. So you have 22 plus 78 equals the 100 mils of the gas solution. Okay, so I think that that's pretty clear. You have 22% by volume of the oxygen and inert gases, which are denoted here in this problem as other. Again, ignore this poor English here. I'm going to fix that, and the 72 should be 78. So I'll fix that on the slides. Concentration, mass per volume. What does this look like whenever we're talking about this kind of percent? Well, again, you're talking still about the percent solute per solution, and you're still using the percent expression where you have part divided by the whole times 100 because it is percent. Mass volume percent is usually denoted by M per V, okay? So mass per volume, grams of solute versus mils of solution. So now we're using, mass and a volume, units here, multiplying by 100, and this is what we're trying to talk about. Almost like this would be applicable to electrolytic solutions, to glucose in the blood, for instance. You have gas dissolved maybe in a fluid, including even blood, metals, and say for instance the brass alloy, all this kind of stuff. So let's use an example where we're probing the 0.90% sodium chloride physiological fluid. How would you prepare that? To prepare that, you would start with, and you would recognize what you need. You have 0.9 mass per volume sodium chloride. So whenever you see this in the question, how would you prepare this 0.90% fluid? Know that it's going to be a mass per volume problem, and know that that 0.9% refers to a mass volume percent. In doing so, you know that you're going to have grams per mil, grams of solute per mils of solution, multiplied by 100 to give you that solution. So in this case, you're looking at grams of sodium chloride per 100 mils of solution, probably water, if you were to prepare this brand new, right? So divided by 100 or multiplied by 100 because it is percent, but you can figure that out because the grams here, the hundreds are going to cancel, right? You're going to be left with 0.9 grams. That's the amount of sodium chloride needed per 100 mils of solution. What's another example? Again, there's a lot of them, right? Again, parts solute per part solution. You have percent expression, part per whole times 100. Here is the problem. What is the concentration of a 500 ml solution containing 35 grams of sodium chloride? Well, if we're looking at 35 grams of sodium chloride and we're talking about a solution, a 500 ml solution, then you should know, based on the variety of the different concentration formats that you're talking about mass of the solute versus volume of the solution. So you know that your grams solute is the sodium chloride, and you can set up your expression accordingly. You also know that the solution will be the solvent, exclusively the solvent, 500 mils of water. So you can calculate what that concentration is by simply, looking at 35 grams sodium chloride. If it's going to be percent per volume, then it's going to be 7% mass per volume of sodium chloride, okay? How many grams of fat are in 250 grams of 2% milk? This is the next problem. To do this problem, we have to, again, understand that the milk fat occupies, 2 grams of that entire milk solution. So you're left with a solvent of 98 grams of non-milk fat milk solution, right? So you have 2 grams of solute, which is attributed to just the milk fat. Again, solute equals milk fat, and the solution is the milk fat plus other non-milk fat components. That's giving rise to that, solvent part of the solution. So you know that that's 2%, and that's either mass per mass or weight per weight. I mean, either, however you want to express that, but that is a mass percent with the 2% milk. Okay, so we got, the 2% down. We know that there's 2 grams of milk fat generally in that 2% milk, but now we need to set up a ratio in order to determine the grams of fat in 250 grams. Okay, 2 grams milk fat per 100 gram milk solution. That's the definition of 2% milk. So you start with that and you set that up to, okay, well, how many grams then are there in 250 grams of milk solution? You see how we're doing that? So you had 2% milk as such, and now you're just trying to figure out what this percent milk, or not percent, but how many grams, are, how many grams of fat, or essentially milk fat, are in 250 grams of that 2% milk. So you have 5 grams of milk fat if you work out that expression. So 100, right? You have 250, take that to the left-hand side. 250 times 2 is 500. 500 divided by 100 is 5. So that's how you would perform that calculation. Now, with respect to the blood panel concentrations, this is where things can maybe get a little bit interesting. Sometimes it's not as clear whenever you're seeing these types of units, like these, what's considered to be milliequivalents. Okay, sometimes they toggle between equivalents per liter or milligram per deciliter, depending on what component that they're talking about. So if it's sodium or chlorine, for instance, chloride, I should say, you're going to have this normal range. It's going to be expressed in terms of milliequivalents per liter. And then you also have like glucose, cholesterol that are expressed in milligram per deciliter. And then if you're talking about hemoglobin, then you're going to be talking about grams per deciliter. So let's take, and all of these are generally going to be mass per volume units. Again, as a reminder, the mass per volume unit is gram of solute, or in this particular case, equivalents per milliliter of solution, or it could be liter of solution if you're talking about equivalents, okay? So that could be, again, this just shows you can use this for salts, sugars, everything, okay, that we had discussed before. Let's take a closer look to see what this is going to look like. Some typical concentrations of electrolytes in blood plasma will have this kind of formulation, if you will. You might have one particular solution that contains cations having 138 sodium, 5 potassium, and I'm talking about milliequivalents per liter here as the unit. 3 milliequivalent per liter of magnesium, 4 for calcium, they total 150. 150 total milliequivalents per liter. Notice how these just added up. 138 plus 5 plus 3 plus 4, okay? Same thing with the anions, but separately, the total down here is 150. 150 milliequivalents per liter. In this particular case, you're looking at chloride of 110, bicarbonate 30, phosphate, right? You have 4, proteins 6, which is interesting that they would lump in proteins, but if they're going to be perhaps negatively charged, that's why they did so. So what you can do is you can actually reference this to actually physiological solutions that are available. So here's one that has 0.9% sodium chloride, and the ratio here is 1:1 for the sodium and the chlorine. You have 154 sodium and 154 chloride with a milliequivalent per liter. Where is this used? Fluid loss replacement. How about a potassium chloride and 5% dextrose solution? So this would be treatment for like malnutrition or low potassium levels. You have potassium and you have chloride, they're in a 1:1 ratio, right? Because the oxidation state of potassium is positive, chloride is negative. It's a 1:1. +1, -1. Something called Ringer solution. You can use this. This is a fluid and electrolyte replacement due to dehydration. Sometimes this is also used in laboratory levels if you're going to probe different types of responses, but whatever you're looking at, something biological to, you know, in the environment, in a laboratory or in vitro environment that would be kind of reflective of a true physiological solution. You can always use Ringer solution or other solutions. There's several different ones, and researchers use different ones depending on what they're trying to accomplish, what they're trying to attest and whatnot. But in this Ringer solution, you'll have sodium, potassium, calcium, all having these milliequivalent per liter with 155 milliequivalent per liter with a chloride. Here's a maintenance solution with 5% dextrose. Again, because this is called a maintenance solution, you can guess that it's going to be a maintenance of fluid and electrolyte levels. You know, you have sodium, you have potassium, you have chloride, you have lactate, right? And then you have some hydrogen phosphate there. And then you have extracellular replacement solution. So this is obviously without, you know, outside the cell. This would be very close to having kind of like a physiological fluid as well, because you're going to have sodium, potassium, calcium, magnesium, chloride, acetate, and citrate. So this is the case. If you're going to ask me about the Gatorade formulation, well, that's going to be a secret, right? I mean, we could always do those analyses, and scientists know this, but they know that there's sodium in there, they know that there's chloride in there, and there's going to be other ions in there too. All that have been, you know, scientifically combined in order to give the best, you know, rehydration or, you know, replacement of lost electrolytes, you know, to one's body. But all of those, you know, sometimes you can get into trade secrets or just company specific recipes. That's all part of, you know, the manufacturer or entity that's responsible for those. So we're introducing all of this equivalence. What does that mean? What does an equivalent, you know, and how would we even calculate that? Well, here's a table here, and this kind of helps you. Basically, and in summary, all you do is you look at the oxidation state or the ion state of whatever you're talking about. If you're talking about a sodium cation, the positive is reflects 1 equivalent per 1 mole of sodium. With the calcium, it's 2 because it's +2, right? The oxidation state or the ion state is +2, so it's 2 equivalent calcium per 1 mole of calcium. If there's for every 1 mole of chloride ion, if when charged, it has a -1. So it's just going to be 1 equivalent of the chloride per 1 mole of chloride. And then of course you have 2 for the sulfate here, equivalents of the sulfate ion species, right? The anion per 1 mole of that sulfate entity. It's per 1 because in front of each of these ions, whether it's sodium, calcium, chloride, or sulfate, there's only 1 there. So in looking at a problem, we can get a better feel on how to use this. So here's problem 8.8. How many equivalents of calcium ions are present in a solution that contains 2.5 moles of calcium? Well, to answer, you must know the equivalents of the calcium. You know that it's a 2-to-1 ratio, right, of equivalents per mole of calcium. If you're starting with moles or of calcium, then they're giving you that, then you're solving for the equivalents. And so you can either put it on the right-hand side or left-hand side. It doesn't matter. I usually like to start with the left-hand side, where I would put equivalents on the left and then solve it and put everything there. But here I flipped it around. I just said, okay, I know I'm starting with 2.5 moles of calcium, and I just set up the stoichiometry, that dimensional analysis correctly. I just say, all right, well, it's 2 equivalents of calcium ions per 1 mole, so it's not complicated. It's 5 equivalents. Problem 8.9, a Ringer solution, which we just talked about. For IV fluid replacement has a concentration of 155 milliequivalent chloride per liter of solution. If a patient receives 1,250 mils of Ringer solution, how many equivalents of chloride were given? To set that up, again, you must understand that an equivalent also scales as milliequivalent, by that factor of 1,000, and you can set it up. So you're looking for the equivalent. So you can put all that on the left-hand side. So up above here, when I did it for the calcium, I put it on the right-hand side, equivalent calcium, like that's ended up what we solved for. But if I just took that equivalent calcium, put it all the way on the left-hand side, put the equal sign in, and then proceed with the 2.5 moles times yada, yada, yada to get to that 5, I could have done so. Here it's the same kind of thing. I'm looking for equivalents of chloride, so I could have said equivalent chloride equals, and then this is what I'm entering into, the 155 milli equivalent, because that's what is in this this solution, this Ringer solution per liter, right? So you start off with that. You also know that you have to get equivalents instead of milliequivalents. So there's a dimensional factor involved in there. You know that liter and milliliter, they also scale. Why did I introduce this? Because we're given 1,250 milliliters, which is there. So, I mean, if you can do this without having to do all of this conversions, and that's fine. I'm just trying to be pedantic about it to show where these numbers are coming from and where they're going. But you're going to end up with 0.194 equivalent of chloride, or if you want to use the units of milli, then that'd be 194 milli equivalents of chloride. So hopefully that is making sense. Parts per million or parts per billion. This is another very common unit that is used to discuss concentration. Again, it's still solute per solution, okay? And this time it's scaled by a factor of 10 to the 6 if it's parts per million, or 10 to the 9 if it's parts per billion. The parts per million is discussed as follows. It's the grams of solute per mils of solution times 10 to the 6. It's also milligram of solute per liter of solution times 10 to the 6. Okay, 1% weight or per mass or mass per volume is equivalent to 10,000 ppm or 10 to the 4 ppm. This is a really useful conversion to know. It's not typically talked about too much, but if you're in an environment where you're having to know and having to relate the percent or the amount of active ingredient that you're talking about, and you want to know that with respect to ppm, especially if you're measuring out some things, this is where that can actually provide a benefit of knowing that 1% equals 10,000 ppm. It's just a shorthand abbreviation. I like to use it in my research efforts, and I just wanted to introduce it here because I think it's quite useful. Parts per billion would scale similarly to the parts per million. Instead of 10 to the 6, you'd have 10 to the 9, right? Because 10 to the 9 reflects billion, 10 to the 6 million, 10 to the 3rd, right, is the 1,000, right? We just, keep on going there. So there's nothing different here, but where would you expect to find the parts per billion and parts per billion? Well, this is used for active ingredients, that, like I just mentioned, but also for contaminants and toxicity. So for instance, if a 1,250 ml solution comprises 15 milligrams of lead, denoted with chemical symbol, as you guys know, PB, what is the ppm of lead? Well, how you would set this up, you're looking for the ppm of lead, so I put that here on the left-hand side. You know that you have grams per solute, right? Grams of solute per mils of solution. You already know that you're starting with this. Now, I could have easily have used milligrams per liter, but I decided to use grams per mil, so it was just a matter of choice. Remember that you have to include that 10 to the 6 factor, okay? So you have the grams per solute per mil of solution times 10 to the 6, so that's 15 milligrams of lead versus 1,250 mils of solution times 1 gram is 1,000 mig, right, or milligram of lead. There's that conversion factor times 10 to the 6, so that comes out to be 12 ppm of lead. So not that hard, but this is a great example to show what this means and how you would read that. If you were to communicate with somebody, you would say that it's 12 parts per billion, 12 parts lead per million milliliter, which sounds just absolutely silly. That's why you just say ppm, 12 parts of lead ppm, or 12 ppm of lead, either way. But again, this is just for emphasis there. So here's a bit more about ppm. It's defined as concentration of solute per million solids, liquids, or gases, right? So we talked about all this, and here's all this kind of involvement. If you have, if you start with milligrams of solute solution and you're trying to get to grams per million, you can do that times 10 to the 6. It's a unit of density with parts per million. So this is really interesting because when dealing with solids, when we're talking about soil, like if you're an environmental chemist or you're wanting to know about the contamination of, X amount of bad agent, that's causing some kind of endocrine interruption, whatever, or if you're talking about some kind of contamination with the food, or if you just want to know what the vitamin intake, or vitamin concentration is within a given food, or even mineral or whatever, then, you could use this relationship to reflect mass instead of volume. So this is where this is important. And again, because it's a unit of density, you can actually get to milligrams of solute per liter of solution, realizing that 1 liter solution equivalent to 1 kilogram of solids. Again, don't forget the 10 to the 6 factor, but this is where you talk about milligrams of solute per kilogram of solids. Again, we're talking about solids here. So liquids and gases, not necessarily necessary, but whenever we're talking about solids, it is. So again, using that ppm relationship, sometimes it's also referred to as 1 milligram per kilogram, okay? It's used for composition, active ingredients, contaminants, and toxicity. For instance, here's a table, 6.1. I just pulled this out of a Metal Contamination in Food, 3rd edition, 2002 book that these authors put together. They summarized really the lead content of foods in different countries and look at the units that they're using, milligram per kilogram. So again, this is a very common unit that you can expect to see over the course of your life, in the nature of your major. If you're looking at food then, say cereals, meat, fish, dairy products, vegetables, for instance, you can look at, in Canada here, it's about 0.012 milligram per kilogram. So that's the ppm. So it's actually on the ppb, in the parts per billion level. It is so low here in Canada, the lead content in cereals, that we're actually in the parts per billion level. Look at the dairy products. It's actually the range in Canada for lead content is about, as the least amount is 1 part per billion, okay? In Spain, it's less than 5 parts per billion. In Japan, for the dairy products, it's about, it's a little bit higher, right? It's about 32 billion parts per billion. And in the UK, it's much less. The UK has very strict levels of lead, but so do these other countries. They just happen to be even a little bit more specific with respect to what those levels are. So anyway, 1 ppm is equivalent to 1 milligram per kilogram unit, okay? Again, this is used for composition, active ingredients, contaminants, toxicity, especially when we're talking about solids. This is also the case when discussing active ingredients in toothpaste. So here's the Clean Pro tooth cream. This is one of the toothpastes that 3M markets. It's 3M Oral Care. It used to be 3M SB. It might still carry that kind of title there. 3M SB, 3M Oral Care, they're all essentially the same entity, although SB is the German counterpart that is responsible largely for the oral care business. But anyway, I'm digressing here. You see that there's 0.21% sodium fluoride that's listed on this product packaging. So this is just the, one of the product packaging inserts that have been communicated to the National Library of Medicine and whatnot. It's just good it's just good manufacturing and just good salesmanship actually to provide all this information. Anyway, you can see the different levels of this product packaging here. This Clean Pro tooth cream is available here in the United States. This version looks a little bit different. And obviously you have all these kanji characters and stuff that's sold in Asia. For instance, this is a version of it. And if you're really keen to it, if you look at the inactive ingredients in that upper left Clinpro tooth cream labeling, you can get to the end of it and you'll see tricalcium phosphate is listed. That is the version of the calcium phosphate that I created that has been incorporated into this product, and that is also present in the other versions as well. Anyway, the active ingredient is the sodium fluoride, 0.21%, and they also have it in parentheses here, 0.12% weight per volume fluoride ion. So among all those different concentration units we have, that would be one example of what that looks like. So if the whole tube here weighs 113 grams, which it does, if you go back up to that upper left image of the Clinpro tooth cream, you'll see contents 1 tube, net weight 4 ounces, or in parentheses there 113 grams. That's where I'm getting this 113 grams from in this question. The question poses, if the mass of the toothpaste is 113 grams, how many grams of sodium fluoride, which is the salt form of the active ingredient used, does 1 tube of toothpaste contain? Furthermore, what is the ppm fluoride? So how do you figure this out? You know that 0.21 weight per weight. Again, even if it's weight per volume, it doesn't matter. It's essentially talking about the same thing. What you're looking at is X amount of grams of sodium fluoride per 113 grams of the total toothpaste, because that's the total amount. So you know that if you solve for the X, right, you already know what the 0.21 is. Remember, divide by 100, multiply by 113, then you'll get the number 0.2373 grams of sodium fluoride. Now, the molecular weight of sodium fluoride is 23 gram per mole, which corresponds to sodium, plus the 19 gram per mole, which corresponds to fluoride. Overall, then it's 42 gram per mole. So you know what the total molecular weight is. You know what the mass, right, of the sodium fluoride that's added. You're still looking, right, for the ppm fluoride. So the 42 grams per mole with respect to the percent weight of the fluoride is 45%. How do you figure that? Well, 0.21 times the ratio of 19 over 42. Again, this is the ratio of fluoride per sodium fluoride. That's going to be equal to 45, just 19 divided by 42. Okay, that's the percent weight fluoride. If we were to look at that, because I'm dealing with, you know, with the percents, just got to make sure that we have the right units here. So you're looking at then 0.0945% weight of the fluoride ion itself. You multiply that by the 10,000 ppm per 1 weight percent, that relationship that I introduced on the previous slides, and you'll come up with 945 ppm of fluoride. This is how much is there. So the US monograph, the FDA monograph states that over-the-counter toothpaste can have up to about 1,100. I think it's actually between 850 and I believe 1150. It might even be a little bit higher than that for over-the-counter sodium fluoride containing dentifrices or toothpaste. And so this is an amount that falls within that range. And you are expected to have that kind of testing to make sure that that amount is still available. Why? Because fluoride, especially when delivered from sodium fluoride, is the active ingredient. This is a drug product. Toothpaste that contains fluoride is not just a cosmetic. This is an active drug, product that delivers a health benefit. What is the health benefit? It's an anti-caries benefit. It helps prevent cavities. Next, and we're almost done here, we're talking about dilution. So knowing that, I think in some of the other examples where we looked at milk fat and then 250 grams of the milk solution, how much fat was that? We had to set up a ratio. That was several slides previously. Here we're doing the same thing. We have concentration times volume, and the initials are going to be consistent with the finals if we're setting up this dilution. So the solute is fixed, but only the volume changes. So for instance, if you had canned orange juice and you had to make it, right? So you get the cons or the concentrate of the orange juice, you put it into a pitcher. Here, 1 can of orange juice concentrate, 3 of them you can put in there of water, right, to get that solvent up there, and then you just mix it together. Overall, there's a total of 4 cans, right? You can actually figure out what that concentration is. Here's an example. What is the final, not using orange juice, but something different? what is the final concentration if you diluted 150 mils of this 0.9% sodium chloride fluid, which you guys now know is a common physiological fluid, to a final volume of 450 mils. How would you set that up? Well, use a ratio. You have 150 mils as your starting, so that's your initial volume. You have 0.9% as your initial concentration, right? You want to know what that concentration is going to be at the final volume of 450. So you know your V final is going to be 450, and you're looking for your concentration in this particular expression, your X of that. Just do the just do the math. I mean, you already have the ratio set up. You know that you're going to get a 0.3% sodium chloride concentration when it's been diluted to a final volume of 450 mils. So I think that's pretty good. Here's a dilution example and dilution factor. So hydrocortisone is used as an anti-inflammatory for localized pain. You must prepare 50 mg per mil solution of hydrocortisone for an infection. You have 5 mils of a 200 mg per mil hoarded hydrocortisone stock solution available. What do? You first have to recognize the fact that, well, you want to prepare a 50 mg per mil solution of the hydrocortisone. Look what you're starting with, a 200 mg per mil hydrocortisone stock solution. Which one's more concentrated, the one that you have or the one that you need to have? The one that you have. So you're already starting with a highly concentrated hydrocortisone stock solution. When I say highly concentrated, it's only 4 times as big, but that's still more concentrated than what you're asked to prepare. So you're starting with a concentrated solution, and you need to work your way down to a less concentrated one. How do you do that? You have to use dilution, okay? And you will further understand that you would dilute this with water, okay? You could probably use other solvents, but one of the more biologically friendly solvents that we're all very familiar with, especially if it's going to be delivered into the body, is going to be water. So you start with your 200 mg hydrocortisone per mil solution. You know that you have 5 mils of it, right? And you know that you need to get 50 mgs of it. So what is the volume that you're going to need to have? You're going to need to have 20 mils. So what is that 20 mils going to comprise, right? It's going to be comprising then water, okay? So if you add then 15 mils of water, you will get that total volume to get the 20 mils. Okay, by what factor was the hydrocortisone in the preceding slide diluted? Here's where we're going here. We have the dilution factor. You have V final versus V initial. You have 20 divided by 5, and we know that we have a factor of 4. So the dilution factor was 4. That is what it was diluted. Of course, it makes sense. You started with 200 grams of the concentrated hydrocortisone. You want 50. You know that that scales by 4. So that's not unreasonable. If you were to say, well, look, what's a dilution factor of 1 to 200? This is what that would look like. V final over V initial, 1 over 200, okay? So suppose in this particular instance, a pharmacist has a 200 times stock solution that needs to be prepared, a 500 mil of a 1 to 200 solution for a patient. How much stock solution should be used? So this is just, again, just getting familiar with what these questions are asking. Fortunately, you already know, right? So you have the dilution factor is 1 over 200. That should be equal to the volume final versus over the volume initial, right? That you already knew. So you have 500 mils per volume initial is 200 then, if that's what you're looking for, because that's your dilution factor. Whoop. If you just follow that stock solution, your V initial, then you can do the math, then you need 2.5 mils. Where did I get that 200 from on the right-hand side? It's because you already had a 200 times, 200x stock solution, okay? So that's where we're going with this. And knowing that you have your V initial being much smaller, right, 2.5. If you do 500 divided by 2.5, you're gonna get to that 1 over 200 solution. And so that's where I'm getting that. The 1 colon 200, that's where we're getting that. So you can work that out. Hopefully this makes sense. But these are the type of questions that I think Mastering Chemistry is going to give you. These will be on the exam, and this actually concludes then the rest of the chapter. So that's it for chapter 8, and we'll be introducing chapter 9 shortly. So again, thanks for your attention. Hope this is helpful. If you have questions, you can write to me about it, okay? All right, thank you. Bye-bye.